Hello and welcome everyone. My name is Melisande and it is a great pleasure to greet you all on behalf of the organizing team of AI Helps Ukraine for our 8th talk of our online series. So today we're really happy to have with us Professor David Rolnick, who will talk about machine learning in climate action. And before we introduce our speaker and start with the talk, and while we let more people join in, we'd like to say a few words about why we have organized this charity conference, AI Helps Ukraine. So, hi, Alexei.
Hi, Mele. Yeah, thanks for the introduction. Hi, everyone. I would like to take some time and briefly introduce this conference, mostly to the people who just joined us today for the first time. So AI Helps Ukraine is a student-led fundraising conference in AI. Our goal is to bring together the leading experts in the field of AI and to raise funds for humanitarian help for Ukraine. We're hosting a series of online talks through the months of November and December. And there will be also a full-day in-person event on the 8th of December here at Mila. And you're all very welcome to join. The registration for the in-person event has opened now. We opened it today, and you will soon be able to find the link for the registration on our website, but also on our social media. So it's been almost 10 months since Russian invasion in Ukraine began, and the level of death and destruction and suffering for civil population is very large. No one in Ukraine is left unaffected by this war, and these are just normal people living there, having their normal lives until the 24th of February of this year. So within the last 10 months, around 13 million people have been forced to leave their homes, and an estimated of 18 million people will need humanitarian aid. And the Ministry of Health of Ukraine estimates that 15 million people will require psychological support. More than 15,000 civilians have been killed or injured, and this number has grown from yesterday a lot, for example, after the last severe missile attack that took place yesterday. And so here, for example, on the right-hand side, you see some pictures from the Kiev region, and the upper picture is from my own neighborhood. And so critical civil infrastructure is a common target of Russian attacks, especially now as winter approaches. And so hundreds of thousands of people lack food, water, heat, electricity. And I know it directly from my friends who are sitting there, spending nights without heating and without electricity. And so for this reason, we're asking you to help to support this cause through your donations. And these donations will be used to purchase things like this device that you can see on the left-hand side. So this is a negative pressure wound therapy device. And these devices are especially needed for injuries that people get from missiles, which happens a lot, unfortunately, still these days. So we would like to especially highlight that it's really not important how much you donate. You can donate like $1 if you want. The only thing that really matters is that you don't become indifferent. And the biggest power is in unity, and our international, we believe that the effort of our broad international community can make the real difference for those in need. And this impact and this difference can become larger with every donation and with every retweet on social media also. Last but not least, we would like to thank also our partners, which are Mila and UAMS, which is an NGO from Toronto, and our corporate partners, Google and Ivado Labs. So with this, I would like to give a word to Melisande, who will introduce our today's speaker.
Yeah, thank you very much, Alexei. So before I introduce the speaker today, let me first quickly mention some important house rules and practicalities. So as always, everyone is welcome to use the Crowdcast chat during the presentation for discussing among each other, commenting on what they're hearing, sharing papers, and so on. So generally, we will not interrupt the speaker for questions during the talk, but we'll have a short Q&A at the end. So we also want to make this virtual conference an inclusive and safe space for everyone. So we kindly ask the audience to help us with this. We have a code of conduct. It's available on our website, and according to it, and to keep things nice for everyone, any hate speech or harmful comments will not be tolerated. So now let me introduce you to our speaker today. We have the great pleasure to have Professor David Rolnick, who is an assistant professor at the School of Computer Science at McGill University and Mila Quebec AI Institute, and he holds a Canada CIFAR AI chair. He has contributed greatly to shaping the field of AI to tackle climate change by developing new machine learning methods as tools for climate change adaptation and mitigation. He's also the co-founder and chair of Climate Change AI and the scientific co-director of Sustainability in the Digital Age. And in 2021, he was named as one of the 35 innovators under 35 by the MIT Technology Review. Now, besides machine learning research, part of his work is also about informing policy decision makers about the potential and limits of fighting climate change with AI. And a few of the organizers of AI Helps Ukraine have the great pleasure to be working with David. So we're all very, very happy to have David Rolnick today to talk about machine learning and climate action. So thanks, David, for being here, and the floor is yours.
Thank you so much for inviting me. This is a fantastic initiative, and it's an honor to be among the set of other speakers who are extremely distinguished. I will try to share my screen here. Hopefully you can see. Not hearing any objections, so I'm assuming that it's going through okay. Yeah, so I don't think that climate change needs very much introduction for this audience. We're increasingly seeing its effects, and they're becoming more frequent and more severe. From historic droughts in Western Europe, Western North America, East Africa, and China this year, to historic floods in Pakistan and Korea, among other places, we're seeing increasingly the heavy hand of climate change. And it's also worth bearing in mind that climate change tends to have a disproportionate impact on already disadvantaged communities and serves to exacerbate existing inequities, geographical and between communities within geographies. But climate change is not inevitable in the sense that many people have already died as a result of climate change, and many more will die regardless of what we do now. But exactly how bad it gets depends on what we do. It's not an on-off switch. We have it in our power to make it either catastrophically bad or less catastrophically bad. And we need net zero greenhouse gas emissions by 2050, according to the UN's Intergovernmental Panel on Climate Change. Now, we are very far from achieving that. That is the goal, to achieve the most catastrophic impacts of climate change, but we are not only not decreasing to net zero currently, we are actually increasing emissions every year, with a slight exception during the height of COVID-19 lockdowns. There is a long way to go. There are many actions that we can take, however, and they encompass both mitigation, which is reducing greenhouse gas emissions, and adaptation, which is resilience to the consequences of climate change. There's also climate science, which refers to actually understanding and modeling the climate. So these are the broad areas that one can think about in terms of action, but there are many different specific areas of impact, ways that one can be involved in mitigation or adaptation. So I'm going to be talking first at a high level about how machine learning can be relevant in helping tackle climate change. And this is using a taxonomy that we've developed in this paper called Tackling Climate Change with Machine Learning. I'm going to go through this taxonomy very briefly. If you're interested in more details, I do encourage you to check out the full paper, which is about 100 pages long. There are interactive summaries of it online, though, if you don't want to wade through the whole thing. So in this paper, we touch on the many different ways that machine learning can be relevant across different sectors relevant to climate action, from electricity systems to land use, that's agriculture and forestry, to transportation, to buildings and cities, heavy industry, climate modeling, and many other areas. And in each of these cases, there are many particular opportunities for machine learning, which you can see illustrated here. Not expecting you to go through all these figures, but I can highlight a few and the broader themes into which they fall. The first theme that we see for how machine learning and AI can be valuable in climate action is improving operational efficiency. So that can mean many different things depending upon the sector that you're in. But examples include taking HVAC systems, that's heating and cooling systems within buildings, and optimizing them to use less energy. That can take the form of smart thermostats in personal houses, or more complicated control systems in industrial or commercial building settings. Another example here is steel and cement manufacture. The steel and cement industries together account for between 10 and 15% of all of global greenhouse gas emissions, which is an enormous amount, truly enormous amount. By comparison, all of ICT, so the digital technologies, account for only about 5% max of global greenhouse gas emissions. So there's huge opportunity in steel and cement to reduce emissions just by making things even slightly more efficient. And machine learning is increasingly being used in these industries to reduce the operational energy and greenhouse gas emissions associated with these forms of manufacturing. The second theme I want to touch on is gathering information. Taking some large unstructured data set and parsing it to pick out useful information. So for example, this is often done with satellite imagery for various different purposes. If you have satellite imagery and you would like to understand where forests are being cut down in real time, that is something that machine learning can do much faster than a person can do. Similarly, if you want to estimate carbon stock, which is the amount of carbon stored in a particular piece of land, this is important for incentivizing landowners or custodians to use land in a way that is helping store carbon. So estimating carbon stock can be done from satellite imagery using machine learning, and increasingly is being done as part of carbon pricing systems. Similarly, with natural language processing, there are fewer applications perhaps of natural language processing than computer vision, but it is being used in parsing large textual corpora. So if one has corporate financial disclosures and one would like to pick out information relevant to climate change, like where a company sees itself being vulnerable as a result of climate-related events. That can be really important in shaping policy. And often gathering information is useful because it can help shape policy or other kinds of decisions being made by public or private entities. Forecasting. Often there are time series which are relevant in climate action. A couple of examples I want to touch on here involve the electrical grid. So in order to make sure that the electrical grid is working correctly, you need to have the amount of electricity being produced at any given point in time match the amount being consumed. However, the amount being consumed varies from moment to moment. And the amount being produced does as well if you're using solar and wind power, because the sun can go behind a cloud or the wind can stop blowing. And so both predicting supply on the basis of weather patterns and predicting demand are really important. And we're increasingly seeing machine learning being used in both of these cases with different kinds of data. So for nowcasting supply, you might take, for example, images of clouds and time series data, whereas for predicting demand, you might take just time series data. This has been introduced particularly fruitfully, for example, in the UK's national grid, which recently introduced a new machine learning algorithm that cut the error in the demand forecasts by half. Speeding up simulations. I'm often asked if machine learning can just simulate the entire Earth's climate. And sort of, but there isn't generally a need for that. There is utility, however, in taking the models that we have, which are based on physics and are extremely accurate, and making them run faster. Because oftentimes traditional climate models actually take months to run, even on supercomputers. And so taking pieces of them that are particularly slow and emulating them using machine learning, so speeding them up, coming up with fast approximations, can be extremely valuable. Similarly, in other settings where there are accurate but slow physics-based models, for example, in grid planning on the electrical grid. And we'll see some examples of this later. accelerating scientific discovery is the final theme that I want to touch on here, which involves, for example, suggesting materials for climate tech relevant applications. We need materials, new chemical materials for use in storing energy in batteries, and for use in generating usable electricity in solar cells via solar perovskites. And AI and machine learning can help in learning from past experiments, distilling that information, and making suggestions about new experiments that would be worthwhile to try in the lab to speed up the iteration process and hopefully shorten the time to actually discovering important new materials. So with all of these themes being touched on, I want to dive more deeply into examples from our own work here at Mila. But before I do, let me touch on some general themes. I want to first highlight that machine learning is not just useful in helping tackle climate change, the opposite is true as well. Through looking really closely at what people need in these various different domains of application, you can actually find extremely valuable problems driving fundamental machine learning innovation. So the interplay goes both ways. Some particularly important areas of work in cutting-edge ML that are motivated and guided by domains of application relevant to climate change are hybrid physical models. We've seen many situations in which there's an interplay between machine learning and some known physics of a system, whether that's the electrical grid or the climate and weather or something else. The aerodynamics of cars being another example. Integrating this kind of physical knowledge with machine learning can be extremely valuable, but it's currently very difficult, in particular for deep learning methods. So this is an active area of work within my own group and others. Transfer learning and meta learning. There are many situations in which one needs to transfer insights from one data set to other data sets for various different reasons. For example, if there are geographically imbalanced data, which we'll see later, and one would like to have a more geographically equitable algorithm that functions well, regardless of the setting from which the data is drawn, since oftentimes under-resourced locations will actually be, there will be less data available to develop algorithms, but just as much need for those algorithms to function well. Interpretable and causal machine learning, whenever you're using machine learning in a context where it might be guiding decisions by policymakers, or even in an industrial context where there's maybe mission critical equipment which cannot go down, you would like to ideally have an understanding of why decisions are being made, potentially with causal relationships as well. And understanding as much as possible about why decisions are being made or predictions being made by machine learning algorithms is extremely valuable. Uncertainty quantification. Similarly, you don't want to have a prediction being made by a model without any idea of how confident the model is in that prediction. So really quantifying and calibrating uncertainty correctly is extremely important. And there are many other areas of cutting-edge machine learning where important test cases and insights can be drawn from climate-relevant applications. However, I should emphasize that sometimes simple methods are sufficient. In fact, this is probably generally the case. One shouldn't leap to using transformers when random forests or linear regression will do the trick. One should always start out with the simplest methods possible and see whether they work. As a machine learning researcher, I try to pick problems that I suspect will need innovation while still trying the simplest methods possible to attack those problems. If the simple methods work, then that's great. One can then move on to other areas which might be more in need of machine learning innovation. But coming up with a more sophisticated algorithm than is necessary is counterproductive for everybody. Always try simple baseline. Some broader considerations. Machine learning is not a silver bullet. It's not going to magically solve climate change. In fact, it's only relevant sometimes across all of these different areas, and it's only one piece of the puzzle in every particular application. Machine learning is never going to be useful in isolation from all the other components and stakeholders who are working on one of these challenges. High-impact applications are not always flashy. Oftentimes, the most media-worthy breakthroughs of machine learning are not the ones that are actually most impactful in practice, and certainly not from a climate perspective. We'll see how, for example, self-driving cars are probably making climate change worse later on. and certainly even in the transportation sector, something like predictive maintenance of railroads is more impactful from a climate perspective. Finding failures in railroad lines and maintenance needs may not sound as sexy as working on self-driving cars, but it has a much bigger impact. Deutsche Bahn in Germany is actually doing this a lot now. So there is an opportunity to work on that if people are interested. Interdisciplinary collaboration is really key here. It's important at every stage to scope the right problems, make sure you're working on problems that actually are useful and are framed correctly to address the challenges that people in the relevant domain actually have. Incorporating relevant domain information, it's essential to work with people who understand what information you can build into your algorithm, because if you're starting from scratch with no domain information, that's making your life a lot harder. And shaping pathways to impact. Ultimately, one needs to think about pathways to impact right from the start and work with those key stakeholders to build what they need and to then integrate it into the systems when the algorithms have been designed. If you just publish a cool paper in NeurIPS, that's great, but it is not the end of the story, and it's certainly not how impact is generally speaking achieved. Equity considerations are also fundamentally important at in many different ways. It's essential to empower diverse stakeholders to be working in this area. Obviously, machine learning and AI are areas that already suffer from extreme inequities in who is empowered to work on problems, digital divides, computing, access to compute being a major reason for many stakeholders not being able to work on cutting-edge machine learning. And in climate change, there are similarly significant divides in who is empowered to work on kinds of problems or provided with the resources necessary to do so. And it's particularly important in the climate domain, given the scope of climate change's impacts and the different kinds of ways that different populations and communities are affected. It's fundamentally important to think about also how equity considerations affect the prioritization of problems. We see that, for example, the problems which are talked about very much in machine learning research community tend to favor problems that are of most relevance to certain geographic areas. Like we see a lot of focus on wildfires, which is a really important problem, but it's one that is particularly relevant to North America, Europe, and Australia, whereas we don't see as much of a focus on, say, melting glaciers or locust infestations, both of which are made worse by climate change, but significantly affect geographies like East Africa, the Middle East, and South Asia, which may not have as much resources and power when it comes to moving the priorities within the tech space. And then ensuring data is representative. As I mentioned, if your data comes from one location, you may be designing algorithms that are implicitly working towards that location or that community rather than other data sources. With all those considerations in mind, let's talk about some examples within each of these areas from my own research group here at Mila. Let's talk about first operational efficiency. And so here the example that I want to touch on is constrained deep learning for grid optimization. Balancing the electrical grid, it turns out to require solving a non-convex optimization problem. It looks like this. It's called AC optimal power flow. It's a quadratic optimization problem. The constraints and the objective function are both quadratic, but it's non-convex, which means that there isn't an efficient way to solve this using traditional optimization methods. Since it's so hard to solve and exact solutions take a very long time, typically in practice, people operating electrical grids simplify the problem. They actually linearize it, which, as you can imagine, makes it much simpler to solve, but also gives you something that is very far from the true optimum. And this results in large amounts of wasted electricity, especially actually with solar and wind, because in solar and wind, you have to solve this even more frequently since the constraints are changing. Now, people have tried to use deep learning to address this kind of problem, but typical deep learning algorithms fail. The typical way you would do this would be to add some kind of soft penalty for constraint violation. You would say, I want to minimize my objective function while not deviating from the constraints too much. However, even slight infeasibility is a problem here. If you trade off between the objective function and satisfying these constraints, you end up almost satisfying the constraints, but that's still enough to cause complete collapse of a power grid, because these constraints have to do with the fundamental physics of how power flows within an electrical grid. And so even slight infeasibility makes the algorithm useless. So we've designed a deep learning approach that approximately solves non-convex optimization problems, in particular AC optimal power flow, while satisfying hard constraints, ensuring that you do whatever you have, you always have a feasible solution, even if it's slightly less optimal. So let's look at what goes into this. This is work from iClear 2021, co-led with Priyadonti. The way we've set up the problem is that there's an approximate mapping from some input parameters to some output variables y. The input parameters x parameterize the objective function and the inequality and equality constraints. So you have this family of optimization problems parameterized by x, and you'd like to go from the parameters x of a particular instance to the optimum y. The algorithm looks like this. We take our x, we feed it into a neural network, we output a partial set of variables, complete them to a full set using the equality constraints, correct them so that they satisfy the inequality constraints, and then train the entire thing end to end. Let's look through each component. First, note that we output a subset of the variables. This is because if you are in a constrained setting, you don't have as many degrees of freedom as you have variables. You have these various equality constraints, each of which constrain you to live in a dimensional space that is one dimension lower. You're in some lower dimensional manifold within your solution space. And so what we do is we predict the number of variables corresponding to the dimension of that manifold, and then use the constraints, the equality constraints, to complete the remaining variables. Now, the equality constraint completion process might be done numerically. It might be done either explicitly or implicitly being something like Newton's method. Importantly, though, for when we train this entire thing end to end, we can actually get the derivatives to go back propagate through this by using the implicit function theorem. Because we have these equality constraints, we can work out the derivatives of all of these new variables with respect to the variables that we've already predicted, regardless of how we do this actual completion process, even if it's done numerically. Now we're in the manifold that satisfies the equality constraints. Let's move to the subset shown in blue, which satisfies the inequality constraints. And for this, we're going to do a correction process, which involves stepping along the manifold defined by the equality constraints towards the inequality constraints. We do this using gradient descent. It's gradient descent on the solution, so there's no inner gradient descent going on. For those who've worked with MAML or something else where you have gradient descent inside gradient descent, you don't have to worry about it here. There's no Hessian computation. It's because this is gradient descent with respect to the outputs, not with respect to the weights. And so in a few steps in practice, you end up satisfying the inequality constraints. Now we train the entire thing end to end. We use the soft loss function, which is the objective function plus these deviations from the constraints just to help it train better. So looking through this overall algorithm, we see, again, completion to satisfy the equality constraints, correction to satisfy the inequality constraints, tying the entire thing together by training it end to end. We tested it on a bunch of different domains, convex, quadratic programs, simple non-convex versions of those, which are still impossible to solve using traditional methods efficiently. They break all the convex quadratic program solvers, but can be solved very efficiently using our method. But then the method that we're particularly interested in, the domain that we're particularly interested in is, of course, the power grid optimization problem of AC optimal power flow. And so let's see how we perform in this setting. So we can compare against various different approaches. This is using the soft loss that I mentioned before, trading off between the objective function and the constraints. And we see extreme deviation from the constraints in this situation, which is enough to break the power grid if you were to actually use this. We also fail if we use supervised learning, where we've seen various examples of inputs and outputs, and we try to predict what the output y is going to be on the basis of the inputs x. Supervised learning also fails here. Similarly, if we introduce our correction procedure, that still doesn't make these methods work. And then we try various ablations of our method, showing that all the different pieces are in fact necessary. The important comparison, finally, is with the traditional optimizer, which is a classical optimization technique based on the particular known mechanics of the system. And even though this has been tuned very effectively for this particular system, we are still much better at it in speed. We are 10 times faster, but really 100 or more times faster if you account for GPU parallelization. 10 times doesn't account for parallelization. Deep learning algorithms, of course, are very easy to parallelize on a GPU. So we find that we're basically optimal with a tiny optimality gap while significantly faster. Okay, I'd like to touch on the next example, which has to do with both gathering information and forecasting. We're going to see how this method that we introduced for meta-learning is relevant in both of these different domains. The application area that we're looking at is remote sensing for agriculture, though it's relevant across many different other areas as well. The motivation is that mapping crops and forecasting yield are becoming increasingly important for agriculture and for policymakers concerned with agriculture, as food security is threatened by climate change. Extreme weather and climate events are changing the amount of food yield and the predictability, and can lead to famines across large sections of the world. So having a good sense of what is going on with crops is really important. And machine learning is increasingly being used to do this, but the data required are quite sparse and they're imbalanced across crops and locations. You can see here the data set, one of the data sets that we use from our partners at NASA, which shows in blue all of the points where we have information about whether something is a crop or not. And in orange, the more important information, which is what particular kind of crop it is. And you can see that the orange dots are very, very few places. It's very limited what kinds of crops we have information for and where we have information for it. So we'd really like to be able to use this data, but it's very challenging using current methods. So we develop meta-learning algorithms for remote sensing that can label crops and predict yield and also do other things while generalizing fast to new locations. We'd like to be able to take these locations for which we have abundant data and generalize fast to a new location where we don't have as much data. And this is work led by my student, Gabby Tsang. Now, some background on meta-learning. Meta-learning refers to learning in such a way that the model can quickly adapt to a new task with new data. Many of you have probably seen meta-learning paradigms, in particular model-agnostic meta-learning, MAML, which is a popular framework where a neural network is trained specifically to maximize the effectiveness of gradient updates on new tasks. So you see, in this case, we're moving the model parameters in such a way that they can quickly move to a good parameter regime for task 1, task 2, or task 3 with very minimal additional data. MAML is a training paradigm, so it can actually be run across different network architectures and tasks. And what we're going to do is we're going to improve upon MAML. We're going to make MAML incorporate domain information in order to have it be more effective at generalizing across different tasks in our setting. And so our goal is task-informed meta-learning, where we incorporate task information to improve upon any meta-learning framework. And so the first part of this is the key, which is the learned task encoder. There are many kinds of metadata which are ignored by traditional meta-learning algorithms. We know in many situations in remote sensing something about, for example, where the data is coming from, the lat long of the image. And in the case of agriculture, we also know the crop type. And we can use this information to improve the way that the meta-learner is performing. Remarkably, no one had actually done this in any domain of meta-learning, actually building in this kind of metadata. And there are various ways you could imagine doing it. You could imagine passing it naively in as part of the inputs, but that doesn't turn out to work as well as what we do, which is designing a task encoder that can take this metadata and modulate the hidden representations in the meta-learner using it. So this is one neural network. This is another neural network. This is the traditional MAML model, and so it's a neural network using MAML. And the task encoder simply takes this metadata and it changes the representations using film. So it's modulating with just multiplying by this vector and then adding this other vector. It's an affine transformation on these hidden representations. And this allows the meta-learner to account for what the task actually is. The second component that we introduce is we see that given the huge diversity and imbalance between tasks, it's possible for the model to overtrain, to memorize certain tasks, which will cause it to overfit to those tasks. And so to combat this, we introduce forgetfulness, where tasks that the model has performed almost perfectly on get dropped from training dynamically to enhance generalization in other regimes. So we see that this greatly improves upon both mammal and other kinds of baselines, pre-training methods, random forest. We also compare against various other variations on mammal, like M-mammal in particular, which tries to infer task information while actually ignoring the given metadata. And we significantly outperform all of these methods. It's particularly the case that we perform very well in very small data regimes. So where when seeing very little data of a new task. And so you can see this, for example, in Togo crop versus non-crop, where as the training sample size, the new data that you see in this new task that you have to adapt to increases, most of the models pick up significantly in performance. But TIML, task-informed meta learning, was at high performance right from the start. In fact, it's actually possible to do zero-shot learning using TIML because it has information on the task metadata. Maybe you haven't seen coffee in Brazil, but you've seen maize in Brazil and you've seen coffee in Kenya. So you can generalize better to the new combination of place and crop if you've seen what that place looks like and what that crop looks like in another context. We also do this in crop type class, in crop yield prediction. So that was a classification task. This is a regression task where we're trying to predict what is going to happen next from a time series with respect to crop yield. And we are also significantly outperforming other methods. We see that TIML added on to any method, either an LSTM or a CNN, a content network, it significantly increases its performance. So this is really an addition that can be made to improve the performance of a meta-learning model in the setting of agricultural remote sensing or in various other contexts. So we do improve performance similarly on omniglot and other contexts. And we're working on different applications of TIML in significantly different contexts as well. The third example that I want to touch on is in the theme of speeding up simulations. I'll quickly run through this. And here the motivation is that a particularly slow part of traditional climate models is called radiative transfer. This is a model, this is a way of understanding how radiation passes through the atmosphere, both incoming radiation coming from the sun, it's absorbed by certain layers of the atmosphere, but then some of it is reflected from the Earth, different wavelengths. So infrared gets re-reflected from the Earth, and then some of it escapes to space, but some of it gets absorbed by the atmosphere, which is essentially the greenhouse effect. And so understanding how the radiation passes through or is absorbed by different layers of the atmosphere is really important. But it's time intensive to compute using exact physics, and this is one of the bottlenecks in traditional climate models. This means that climate models have to be run at higher resolution, like a grid scale maybe of hundreds of kilometers, which makes it harder to use the predictions of climate models to inform local or regional responses. If you want to understand how your particular city should respond to climate change, you need fine-grained predictions because the predictions at a coarser level might not be as relevant to you. So we're using deep learning methods, various different kinds, to rapidly approximate radiative transfer calculations. And this is work led by Zalpa Rolnick and Venkatesh Ramesh within my group, and in collaboration with Environment and Climate Change Canada, which is the Canadian agency responsible for modeling climate. Now, we don't just introduce models, we also introduced a new data set. It's 10 million data points from the Canadian Earth System model, which we've curated in a particular way. We also designed it to include out-of-distribution test sets, so pre-industrial conditions, future conditions, and volcanic eruption. This is important because as the climate changes, your models may get less accurate. So we want to understand how accurate models are when they're presented with new conditions. Pre-industrial conditions are very different from our conditions now because there's less CO2 in the atmosphere before the Industrial Revolution. Future conditions, there will be more CO2 in the atmosphere and more greenhouse gases of various different kinds. And then volcanic eruptions just disrupt everything and change the regime of atmospheric gases briefly for a few years. And so we have also a test case like that. Now, the input in our problem setting is gas concentrations, temperature, humidity, and other things at different layers of the atmosphere. We have individual atmospheric columns, so it's like 1D data. And then we're trying to predict different properties also in this 1D column of data, up and downwelling flux, which corresponds to energy change within different parts of the atmosphere, and heating rates per layer. And we try fully connected networks, MLPs, one-dimensional convnets, because remember, this is one-dimensional data, various different graph neural networks incorporating structure of the atmospheric column. We also tried transformers. And we find that in particularly structured models like convnets and graph neural networks allow us to generalize better in out-of-distribution test sets. So we see that these more structured models here, these bars have a lower error as we go into the difficult out-of-distribution cases. Within distribution, all the models perform exceedingly well. But out of distribution, some of them perform quite well, but some of them are are less able to generalize. The effectiveness of our models is extremely high, and they're currently being trialed for incorporation into the Canadian Earth System model because they're just extremely effective across different conditions. And I can talk more about that after if people are interested. We also have an upcoming paper detailing this further, and the physics, how we incorporated physics into these models too. We do work also on the accelerating scientific discovery pillar, including working out better catalysts for use in green energy applications, energy storage, catalysis to and from hydrogen, for example. Unfortunately, don't have time to touch on that now, but again, I'm happy to answer questions on that. And there's work including, for example, graph neural networks that we just released on how to approximate properties of catalysts extremely fast. However, there are a number of overall considerations that I want to touch on before closing. And first of all, I want to highlight how the examples that we've seen speak to the importance of working between machine learning expertise and domain expertise. And I want to talk about what happens when that fails. And by way of illustration, I want to talk about ImageNet. So machine learning continues to rely on data sets like ImageNet that are used in developing models as well as in the research context, as well as developing pre-trained models for real-world tasks. And these data sets were often created in a very computer science-focused way. They were created by computer scientists, machine learning folks, without relevant experts in the room, and often using internet data that was combed from very noisy or biased corpora. And this leads to numerous problems. So let's investigate what happens when you create a data set that is used extensively in machine learning and could be relevant to a certain domain and is often treated as such, but is actually extremely problematic within that domain. So ImageNet turns out to be made up significantly of wild animal photos. 27% of ImageNet is pictures of wild animals, many different species. And we work with ecologists to analyze these images, which were, again, not created with relevant experts in the room. They were found on the internet using Google image search, and they were annotated using Mechanical Turk. So there were no experts in the room in the creation of this part of ImageNet. And this is work together with Sasha Lucioni. Now, the first thing we look at is errors. It's perhaps the first thing you would want to see. How accurate are the images in ImageNet? And they're extremely inaccurate. 12% of the images are incorrect. And some of the classes are over 90% wrong. So for example, the black-footed ferret class, it's only 2% right. Only 2% of the images are actually black-footed ferrets. And there are a number of reasons for this. Two of the main ones are annotated inexperience. There are often very similar images of similar species, which somebody without domain experience is not going to be able to tell the difference between. So for example, herons and cranes, difficult to tell the difference. This is problematic partly because just from an accuracy perspective, the class of herons, it does not just include herons, it also includes some cranes, but also there is a crane class as well. There is a heron class and there is a crane class, or I think it's actually an egret, so a specific kind of heron class and a crane class. And some of the images in one of those classes should be in the other class. So it's not just that these are incorrectly identified, they should actually belong in another ImageNet class. And this is the case across many of these errors. We're seeing inaccuracies where the image should actually be in a different ImageNet class. Another source of error is, for example, nomenclature. There are many kinds of beetle in ImageNet. There are many classes. One of them is leaf beetle. And we see that the vast majority of the leaf beetle images are wrong. And that's because when you do an image search for leaf beetle, you get beetles on leaves, any kind of beetle. Whereas a leaf beetle is actually a taxonomic thing. And it's very clear it's actually called leaf beetle chrysomelid in ImageNet. So they were definitely meaning a particular kind of beetle, but instead they got all kinds of beetles, including the kinds of beetles from the other classes in ImageNet. So again, the images are incorrect, and they should actually often be in other classes. 12% of the classes also conflict with other classes, like tusker, which is a class of elephants with long tusks and overlaps completely with the class African elephant. Meerkat, which is a kind of mongoose and overlaps with the class of mongoose. And indeed, many of the images of mongooses are meerkats. So similarly, we can see images should or can be in a different class from the one to which they are assigned. A number of the classes are also vague and unclear, such as cricket or kite, which mean different things based upon where you are in the world, which takes us to our next point, geographic bias. Because we know what species are from images of them, we can work out where the images approximately were taken. And this is really useful in a way that we can analyze images. Maybe you couldn't work out where a picture of a chair is from, but you can work out where a picture of a bird is from because you can identify the particular species of bird. And so we did that. We worked out where the birds are from, and 58% of them show birds from the US, even though the US actually represents only 8% of total bird diversity. In black, you can see the true biodiversity of birds across different regions, and then you can see in orange the different ways in which ImageNet represents that. So the United States, way overrepresented in ImageNet, more represented than any other region, even though it's actually among the least biodiverse regions. Europe is also overrepresented, though not quite as much. This imbalance is true for choice of classes. So for example, the bald eagle is the only kind of eagle that is in ImageNet, and that is the national bird of the United States, whereas there are many other eagles, many of which are national birds for other countries. And this is also true for mislabeled images, where, for example, we see the goldfinch class is mostly incorrect because instead of one species of bird, it was the American version of that bird. And then I think what is particularly insidious and particularly informative is where we see the imbalances within a certain class. So for example, for the jay class, these are 4 of the 50 species of jays found in the world. They look very different, and they're found across very different regions. This is found in China, this is found across Eurasia, this is found in Mexico, and this is found in the US and Canada. This is a blue jay. And this might be the one that people in Canada, or I don't know where you're dialing in from, but those of us at Mila are probably most familiar with this, but it's actually only found in the US and Canada. 62% of the J class in ImageNet is this one. And you can imagine if you're an algorithm trying to generalize across many different species, you're not going to be able to do that effectively. So really, ImageNet is even when it's correct, it's implicitly biased towards species from particular geographies, which is resulting in downstream effects. I'll get to that in a moment, but I also want to quickly touch on other problems. We see that, for example, fish that people like to catch and animals that people like to hunt are often shown dead in ImageNet. This is a typical image of a fish from ImageNet. It's not a wild fish shown in the wild. It's a person holding a fish. 62% of these kinds of fish are actually images of people holding them. 5% of the images show multiple kinds of animal, 1% are fake, like this stuffed dugong, which is very cute, and 1% are image collages, where the only species here that is the correct species is this one in the corner. Why does this matter? Well, we see many different effects. First of all, we see that accuracy on ImageNet is just not effective. If we're using ImageNet to benchmark algorithms, and we're caring about little tiny 0.1% increases in performance, which we often do, that is really misleading, given the huge errors in even just this one part of ImageNet. Also, it's secretly testing few and zero-shot learning because we have these imbalanced classes, which are actually made up of lots of subclasses, but one class is dominant because of geographic or other bias. We're also seeing the dangers of using ImageNet in any context where pre-training is connected to the final task. So people often use ImageNet to develop wildlife classifiers. There are better data sets like iNaturalist or iWildCam many other different data sets, but people often use ImageNet because it's common, widely known, and popular. So this is really dangerous. We're developing models that, for example, could be identifying species incorrectly or suggesting images to people that are geographically biased and perpetuating this kind of US Americentrism. And it really points to broader failures in the creation of machine learning data sets, which are still often defined by computer scientists, particular sets of institutions drawn from problematic internet corpora and annotated without relevant expertise. And it's really exemplary of how machine learning innovations are often developed without the stakeholders who are relevant to shaping the underlying societal impact. Jumping off of this more, I want to touch on how machine learning is used in many ways that also negatively impact the climate. And for further reading on this, I would point to our recent Nature climate change paper. People often particularly focus here on computation-related impact, thinking about how much energy use is consumed by the computation of a machine learning algorithm, and also the embodied emissions from hardware, how much emissions were generated in the process of making the computers on which the algorithms run. These are important, but they're only part of the picture. And honestly, they're one of the smaller parts of the picture. There are bigger effects, which come from the ways in which applications are applied. We've seen some positive applications of machine learning, but there are also significantly negative, like applications of machine learning in fossil fuel exploration and extraction, or in fast fashion. Fossil fuel exploration and extraction. Machine learning is estimated to contribute to $500 billion in additional profit for the fossil fuel industry by 2025 alone. That is a lot of impact, which is explicitly running counter in most cases to addressing climate change. It's actively serving to help outcompete low carbon sources of electricity. In fast fashion, machine learning is enabling the production of more disposable items of clothing, and the industry, which is resulting in a hugely increased global greenhouse gas emissions and consumption of resources. And then more broadly, there are systemic impacts of applications, which have to do with changes in consumer behavior, for example. Machine learning is being used widely. One of the most common applications of machine learning is in advertising systems. These are explicitly designed to increase consumption of resources. And it's not being measured, but it's doubtless having a much more significant impact than most other applications, positive or negative, of machine learning from a climate perspective, because so much energy in the research space implicitly and in the application space is being devoted to machine learning in the context of recommender systems that are actually driving increased consumption. And then there are applications which can positively or negatively impact the climate, depending on how we're developing the technology. Here I want to highlight autonomous vehicle technology. So self-driving personal vehicles, which is where most of the focus is, are expected to make climate change worse, because if you lower the barrier to driving, you make it easier to drive, people will drive more miles. Each mile driven may become a bit more efficient, but overall the effect is expected to be negative. It will result in more greenhouse gas emissions. There may be positive effects on safety potentially, or other effects, but from a climate change perspective, it's probably bad. But if we focus on autonomous vehicle technology that is designed with public transportation in mind, we can potentially use these technologies to decrease global greenhouse gas emissions. This is an example that really illustrates how we are developing a technology really impacts the way in which it changes the world. And I want to close by highlighting that AI for good doesn't just mean adding new good applications of AI on top of business as usual. It means shaping all applications of AI to be better for society. So thinking in terms of the many ways in which whatever you're developing is impacting society via climate lens or other lenses, rather than just thinking, I will work on this positive application of AI, because every application of AI affects society. I also want to touch on the fact that in comparing these different ways that machine learning negatively impacts the climate, part of the reason why people have been focused on computation is, I think, quite cynically a focus by major tech companies on the part that they can control the most. Nobody really wants to talk about how you're They're developing applications that are explicitly increasing consumption. And so they focus on green algorithms, which use less energy or maybe use renewable energy to power those algorithms without focusing too much on what those algorithms are being used for. So really, the takeaway, focus on what your algorithms are being used for. In closing, I want to also touch on climate change AI, which, as Melly mentioned, is an initiative to catalyze impactful work at the intersection of climate change and machine learning. We have many different resources, reports aimed at different communities, from researchers to policymakers, many different events, including our upcoming workshop at NeurIPS, part of a series at many different machine learning conferences. We also have mentorship programs if you want to submit to a future workshop. And you can see all of our past papers from events at climatechange.ai/papers. We also have a summer school, which will be opening up applications in the coming months. And we also have funding programs. We have a grants program. This is the second round of our grants program, which awards 150K USD to each project in projects at the intersection of machine learning and climate change. We have a newsletter with updates on jobs, data sets, papers, funding opportunities, and other things in this space. And we have webinars and happy hours to dial into the community more. Thank you so much for listening, and I look forward to a few minutes of questions.
Thank you very much, David, for this amazing talk. I found it great to see that impactful machine learning research can be done when applied to this relevant problems of our time, like climate change. So yeah, now we can move to the Q&A session. I would like to also encourage everyone to ask their questions in the Q&A chat on the right. And
Yeah, there's a question right now about a trend of training bigger and bigger machine learning models and incur more and more carbon emissions. Is it worth it? It depends, I would say. I would say that generally speaking, the trend towards bigger models hasn't been motivated by the right things. I feel like in some cases, it's been motivated by relatively minor performance increases. I would also say that some of the ways in which bigger and bigger ML models have been used have also been counterproductive for society in other ways. Ultimately, the failures of large language models have been more, to my mind, in the space of them just being extremely problematic for society in many cases, rather than just thinking about their climate impact. But I would say overall that thinking about the trade-offs is really important. In some cases, there aren't trade-offs. So for small machine learning models, their energy use is relatively insignificant. For really big ones, you should definitely be thinking about this and thinking about whether the performance increase that you anticipate is worth the increase in size. But also, you shouldn't just be thinking about emissions with respect to larger machine learning models. You should also be thinking about equity, because people with lower computational resources at their disposal won't be able to use those large models. And so the more lightweight your model is, the more useful it's going to be, and the lower its emissions are going to be. So all of these things are intertwined. Bigger models have been used in a lot of bad applications, problematic applications, also in some good applications. And one should be thinking about computational efficiency with respect to how much performance increase it actually gives you, and also with respect to equity of resource availability.
Great. Then let's move to the next question. So the next question is about applications of ML for carbon sequestration.
So sequestration can refer to a bunch of different a bunch of different things. Sometimes people could use sequestration to refer to natural carbon capture by plants and land. And I talked about that a little bit, where machine learning can be used to infer the carbon stored in a particular area of land to help incentivize landowners to preserve land or treat it in a certain way that will help sequester carbon via nature-based solutions. There are other ways in which machine learning is being used to help with more sort of artificial forms of carbon capture and sequestration, including identification of storage sites for captured CO2. I know that some of this work is some of this work is quite impactful, but I would also say that some of the same techniques, it's worth noting, are used also to identify fossil fuel reservoirs. So subsurface imaging can be used in various positive and negative ways. There are subtly different algorithms, but it's worth bearing in mind for sort of that area of work. So it's being used both to facilitate oil and gas exploration and also to facilitate carbon sequestration. So yeah, just something to bear in mind. I don't think that that's the most impactful area of application, identifying storage sites. I think the most impactful area of application probably is, yeah, land use and carbon stock estimation using satellite imagery.
Thank you. Okay, the next question is about using climate models for data generation, for generating training data, and how to combine the generated data with the real data, and maybe
yeah. So you can generate data in lots of different ways. You can take real data. You can take completely generated data by a physics-based model, so a traditional climate model. You can also do what's called reanalysis, which is aligning observed data with a physics-based model in order to sort of interpolate what data wasn't observed. Maybe you only have certain stations, so you'd like to interpolate the rest. That's called reanalysis. So all three of these things are commonly used to train machine learning models. Real data, simulated by a physics-based simulator, or reanalysis data, which sort of integrates the two. You could also imagine using a machine learning model to create simulated data to train another machine learning model. This is generally a bad idea because you end up in problems like mode collapse or overfitting to something that's an artifact.
Yeah, maybe related to this. So I know that weather forecasting has been a hard problem for machine learning models for a long time. And climate models were, in my understanding, the model has to predict over a much longer time horizon, is even a harder problem. So how accurate are these climate models are?
So you said over longer time horizons?
I would say in general, a machine learning-based climate model, how good is it?
Well, to be clear, a climate model is more than just sort of simulating every weather event. You're not going to get all the micro scale accurate in order to simulate the macro scale. So there's sort of fundamentally different goals involved. But it's a really good question because oftentimes you're spinning the same model multiple times on its own output. If you're doing sort of time series prediction with a climate model, right? You predict the next step and then you predict the next step on the basis of that. And so if you make errors, those add up. So it's definitely something to be considered. One of the reasons why we've been interested in different error metrics for our climate model emulators is for this reason. If you're interested in short-term prediction, you might be interested in sort of absolute error. Whereas if you are interested in longer-term prediction, you might be interested in bias, because even a small bias over time can add up a lot. So I think that this definitely informs the way that you want to design your models and calculate the efficacy of a model.
All right, makes sense. I think the last question would be, do you think that the machine learning community should shift towards using, let's say, more relevant climate data sets rather than just cats and dogs classification for the research? And if so, how can we make that move?
Yeah, so I think that there should be more, value placed in the machine learning community on using real world data sets and tasks overall. And I think that this is both because we're ultimately working on a lot of the same tasks, which severely limits the kinds of innovations we can produce from a methodological standpoint, but also it means that we're not developing the algorithms that are most useful in practice. And so I would say that with respect to climate, I'd say that with respect to other things as well. And I think that the culture of review, at least in machine learning, is such that oftentimes people get penalized for working on data sets that are less well known, or for tailoring an algorithm to a particular use case. Whereas actually, I think this should be prized a lot more, because oftentimes by looking at a use case, you are not just impactful, but you actually design something which is truly innovative in a way that is maybe more meaningful than getting a tiny little improvement on a task that people know well. So I'd say that there's room for both kinds of innovation. I think that there should definitely be an increase in the extent to which the community values truly applied tasks, which can lead to interesting and useful algorithmic improvements.
Thank you very much. Thank you very much for participating in this event today. So I think we don't have any more questions. I'll just want to remind everyone that the next event will be the in-person event in 2 weeks, and you're all very welcome to register using the link that was posted in the chat. And so, yeah, we'll have a break next week. Everyone or people will go to NeurIPS, so maybe see some of you there. And yeah, have a great weekend. Bye-bye, everyone.